Now let's look at this problem of determining the lowest common ancestor of two nodes in a binary search tree. The key insight here is that essentially if we start traversing this binary search tree starting from the root, and you're given, let's say, two elements for which you want to find the lowest common ancestor, starting from the root, the first time, and doing a normal binary search traversal, the first time we encounter a node such that the two elements are on either sides of that element, that is the lowest common ancestor. So let me just illustrate this with an example. So let's assume, as I said, that we want to compute the lowest common ancestor of 1 and 13. We start from the root and say, okay, well, are both 1 and 13 to the left less than 1? No, that's not the case. Are they both more than 7? No, that's not the case. Then, well, 7 is the least lowest common ancestor. Okay, let's take another example. Let's assume that we have two nodes 8 and 10 that we want to compute the lowest common ancestor for. So we'll start from the root 7. Well, both 8 and 10 are greater than 7, so we move to the right subtree. We consider 12. Well, both 8 and 12 are less than 12, so we consider then the left subtree 9. Well, now 8 is less than 9 and 10 is greater than 9, and so we assert that the lowest common ancestor in this case is 9 for 8 and 10. So in other words, our algorithm, it should be pretty intuitive. Starting from the root, we do the normal binary search tree traversal, where we're comparing the two elements. If they're on one side, we keep searching the subtree, either left or right, and the moment we arrive at a subtree root for which the two elements are on either sides, that's the lowest common ancestor. So let's see how we can express this in a algorithm. So we have LC lowest common ancestor. We're given let's say two nodes A and B, and of course we are given the root node. We check if the root that we are given is equal to null, and if so, there's nothing to do here, so we return null. And of course we are going to have a return value of node, which is the lowest common ancestor that we are going to return. Now, as I said, if both A and B, if A is less than root, well, and B is also less than root, well, then we should search the left subtree. So we say, well, return LCA A and B, and now go and search the left subtree. Else, if both A and B are the reverse, which is both A and B are greater than the root value, well, then we explore the right subtree. Okay, and if A is less than the root val and B is greater than root val, or vice versa, then we simply return the root. Now, the only issue with this algorithm is for a tree of arbitrary size, which is of height h, and h can be a very large number depending upon the size of the tree. We do require space to the order of h, because the recursion essentially can potentially, we need to traverse the tree up till the height, and the height can be large. And so the question is, can we do this with constant space? And that's what we'll see next. Now, to do this with constant space, we will use a non-recursive solution, which will essentially be very similar to the recursive solution logic-wise. So let's rewrite our lowest common ancestor routine with the same parameters. Node A and node B are the elements for which we want to calculate the lowest common ancestor, and we are given the root of the tree. Well, we will essentially traverse this tree starting from this point, which is the root. We'll simply say, well, why root is not equal to null. Well, root is not equal to null. Again, if the element A is less than the root element, and B is also less than the root element, then we simply will address the root pointer or to the left node, else if A is greater than root, well, and B is also, greater than root, well, then root is equal to root dot right. Okay, and else we know that one is less and one is greater, so at this point we will return the root. Now the interesting thing is, it says, well, at the end we will return root, but when would you get to this stage? Well, you will only get to this stage if root is equal to null, because if root is not equal to null, you'll still be in this while loop. So this means that you'll be returning null. Well, what does it mean to return null for the lowest common ancestor? Well, essentially you'll be returning null under the circumstance where essentially these nodes, there's a possibility that one or both of these nodes may not be in the tree. So in this case, you basically do not have a lowest common ancestor, and that's what essentially returning null means.